The morning of March 3rd, 1944, Royal Air Force Station, Leiston, Suffolk, England. The sky is the color of wet concrete, and a bitter wind cuts across the hardstand where a single North American P-51B Mustang sits, its Rolls-Royce Merlin engine ticking as it cools. Lieutenant Thomas Hayes stands beside the aircraft, staring at what appears to be two enormous tin cans bolted beneath the wings. They look flimsy. They look absurd. They look like something a high school shop class might have cobbled together from scrap materials and prayer. Staff Sergeant Benjamin Davis stands a few feet away, hands shoved deep in his jacket pockets, his breath visible in the cold morning air. He's 32 years old, a mechanic from the mountains of North Carolina, and he's just bet his reputation, possibly his career, on those two paper cylinders. Each one holds 165 gallons of aviation fuel. Together, they represent an idea that the finest aeronautical engineers in America have declared impossible. In 20 minutes, Hayes will climb into that cockpit and take off on a flight that will either prove Davis right or turn him into the laughingstock of the 357th Fighter Group. But to understand why this moment matters, why two paper tubes attached to a fighter plane represent one of the most crucial innovations of the Second World War, we need to go back. Back to a crisis so severe that by early 1944, the United States Army Air Forces were quietly preparing to abandon their entire strategic bombing doctrine. Back to a problem that was killing 600 American airmen every week. Back to physics, mathematics, and the stubborn, immutable reality that was losing the air war over Europe. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The crisis had a name, though it wasn't spoken aloud in official reports. Pilots called it the death run. Planners at 8th Air Force Headquarters called it the range problem. General Henry Arnold, commanding the Army Air Forces from Washington, called it by its proper name in a classified memo dated January 15, 1944. An operational catastrophe threatening the viability of daylight precision bombing. The mathematics were brutally simple. A Boeing B-17 Flying Fortress, fully loaded with bombs and fuel, could reach targets in Germany. It could drop its payload. It could turn into a home. What it could not do was defend itself against determined fighter attack. The B-17's defensive armament, 1350 caliber machine guns, sounded impressive on paper. In practice, against coordinated attacks by Messerschmitt Bf 109 seconds and Focke-Wulf 4 190 seconds, it was insufficient. The bombers needed fighter escorts, but American fighters couldn't fly far enough. This wasn't a failure of courage or tactical planning. This was physics. A fighter aircraft in 1944 was fundamentally a fuel tank with an engine attached. Everything else, the guns, the armor, the pilot, was secondary to the basic equation of weight, drag, and range. The Lockheed P-38 Lightning, with its twin engines and distinctive twin-boom design, could escort bombers roughly 400 miles from English bases. The Republic P-47 Thunderbolt, massive and powerful, could manage about 375 miles with its standard fuel load. The newest fighter, the P-51B Mustang, was aerodynamically superior to both, but its internal fuel capacity of 180 gallons gave it a combat radius of approximately 410 miles. Berlin was 600 miles from the airfields of East Anglia. The ball-bearing factories at Schweinfurt were 480 miles. The aircraft plants at Regensburg were 530 miles. The oil refineries at Ploiești, in Romania, were completely unreachable. Every critical target in the German industrial heartland lay beyond the protective range of American fighters. The bombers went anyway. They had to. The entire strategic justification for the daylight bombing campaign rested on the theory that precision attacks on specific industrial targets would cripple German war production. But without fighter protection deep into German territory, the bombers were being slaughtered. October 1943, the month that would be remembered as Black Week, though it lasted longer than 7 days. On October 8th, a force of 378 bombers attacked Bremen and Vegesack. The Luftwaffe waited until the escorts turned back at the German border, then struck in waves. 30 bombers didn't return. On October 10th, a smaller force hit Münster. 29 bombers lost. On October 14th came the second, Schweinfurt raid, a target so critical that planners were willing to accept extraordinary losses to destroy it. 291 bombers launched. 60 were shot down. 17 more were so badly damaged they never flew again. 230 airmen killed, 594 captured or missing. The loss rate exceeded 20%. At that rate, a bomber crew's statistical life expectancy was less than 5 missions. The required tour of duty was 25 missions. Do mathematics. Understand what that meant for the young men strapping themselves into those aircraft every morning. General Ira Eaker, commanding the 8th Air Force, suspended deep penetration missions. For 2 months, American heavy bombers struck only targets within escort range coastal facilities, French rail yards, targets that didn't matter. The strategic bombing offensive had effectively stopped, not because of a lack of bombers, not because of a lack of courage, but because of fuel. Because American fighters couldn't fly far enough to protect the bombers where it mattered. The solution seemed obvious: external fuel tanks. Drop tanks had been used. Since the First World War, detachable containers mounted under the wings or fuselage, carrying extra fuel that could be jettisoned when empty or when combat demanded maximum maneuverability. The British had been using them extensively. American fighters carried them routinely, but existing drop tanks only extended range by 200 to 250 miles. Not enough. Not nearly enough. The engineers understood the problem. Brigadier General Benjamin Kelsey, chief of the Air Corps Fighter Projects Section, had been pushing for larger drop tanks since 1942. North American Aviation, manufacturers of the P-51, had teams working on advanced designs. The British, through the Ministry of Aircraft Production, were experimenting with various configurations. Every aeronautical engineering department in the Allied world understood what was needed: tanks holding at least 150 gallons, preferably more, that wouldn't compromise the aircraft's performance. But here was the catch, the cruel physics that made the problem so intractable. A drop tank isn't just dead weight hanging under your wing. It's dead weight that creates drag. Drag requires power to overcome. Power comes from burning fuel. At a certain point, the fuel you're burning to overcome the drag of carrying extra fuel equals the fuel in the tank itself. You've reached the point of diminishing returns. Make the tank larger, and you actually reduce the effective range. The best minds in aeronautical engineering had calculated the limits. Standard 75-gallon pressed steel drop tanks added about 200 miles of range to a P-51B. Experimental 110-gallon aluminum tanks, carefully streamlined, could add 250 miles. But anything larger created so much drag that the net gain disappeared. Multiple reports from Wright Field, the Army Air Force's primary testing facility in Ohio, concluded the same thing. Tanks exceeding 110 gallons were operationally impractical. There was another problem, equally serious: weight. A gallon of aviation gasoline weighs approximately 6 pounds. A 150-gallon tank, when full, would add 900 pounds of fuel alone, plus the weight of the tank itself. Add that to a P-51B that already weighed 7,000 pounds empty, and you were asking the Rolls-Royce Merlin engine to haul over 9,000 pounds into the air. The aircraft's takeoff characteristics would change dramatically. Its landing characteristics would become unpredictable catastrophically, so if the pilot had to return with the tank still partially full due to mission abort. In November 1943, North American Aviation submitted its formal assessment to the Army Air Forces. The conclusion, signed by Chief Engineer Edgar Schmood: drop tanks exceeding 110 gallons in capacity present insurmountable aerodynamic and weight distribution challenges for the P-51B airframe. Further development in this direction is not recommended. The engineers weren't wrong. They were solving the problem the way engineers solve problems with precision, with advanced materials, with careful attention to aerodynamic efficiency. They were trying to build better tanks. Benjamin Davis, who had never taken a course in aeronautical engineering and whose formal education ended with high school, was about to solve the problem by building worse tanks. Davis came from Wilkes County, North Carolina, in the foothills of the Blue Ridge Mountains. His father, Clarence Davis, ran a small garage in Wilkesboro. His uncle, whose first name Ben, carefully never mentioned in any official capacity, ran a different kind of operation back in the Hollows, the kind that required careful understanding of volatile liquids, pressure, temperature, and what happened when you got the mixture wrong. In Wilkes County in the 1920s and 30s, a significant portion of the local economy ran on that understanding. By the time he was 14, Ben Davis could rebuild a Ford Model A engine with whatever parts were available, which was rarely the parts you actually needed. He could weld, braze, and fabricate. He understood that the perfect solution was rarely available, but the adequate solution usually was if you looked at the problem differently. He knew how liquids behaved under pressure, how containers failed, how to seal things that wanted to leak. These were practical skills, learned by doing, learned by failure, learned because failure in his uncle's operation meant explosion. He enlisted in January 1942, 3 weeks after Pearl Harbor. The Army Air Forces needed mechanics desperately. The expansion of the air arm from a few thousand aircraft to tens of thousands meant a voracious appetite for men who could keep engines running. Davis scored high on the mechanical aptitude tests, low on the academic assessments. He was assigned to technical training at Chanute Field, Illinois, then shipped to England in March 1943 as part of the great build-up for what would eventually become the Combined Bomber Offensive. By October 1943, he was a staff sergeant and crew chief for the 357th Fighter Group at Royal Air Force Station Leiston. The 357th had just transitioned to P-51B Mustangs. Davis's job was to keep them flying, to supervise the maintenance crews, to troubleshoot problems, to ensure that when a pilot climbed into the cockpit, the aircraft would perform as designed. It was technical work, demanding work, but not particularly creative work, until it needed to be. He watched the bomber formations go out. He watched them come back, when they came back, with fighters shot up and men wounded. He listened to the pilots talk in the enlisted men's club about turning back at the border, about leaving the bombers, about the frustration of having fuel for maybe 20 minutes of combat before they had to break off and head for home. He read the intelligence summaries posted in the operations building he wasn't supposed to, but security on a frontline airbase in wartime was more theoretical than actual, and he understood the mathematics of loss. And he looked at the drop tanks. The 357's P-51 seconds were equipped with standard 75-gallon pressed steel tanks, British-made, sturdy, and reliable. They added weight, they added drag, they added enough range to make the difference between turning back at the coast and turning back at the border. Not enough. Davis had seen the classified reports again, security being what it was describing the attempts to build larger tanks. He'd watched the occasional experimental tank come through for field testing, 110-gallon aluminum tanks, beautifully streamlined, manufactured to precise tolerances. They worked, they helped, they weren't sufficient. The engineers were trying to build tanks that minimized drag, minimized weight, maximized efficiency. They were expensive to manufacture. The 110-gallon aluminum tanks cost approximately $180 each in 1944 dollars. They were designed to be recovered and reused. They were built with the assumption that they were pieces of precision equipment that needed to perform optimally. Davis had a different thought. What if you didn't try to build optimal tanks? What if you built tanks that were adequate for a very specific purpose, hold fuel for a few hours, then be thrown away? What if you built them out of paper? The idea came to him in January 1944, though he'd been circling around it for weeks. The 357th had just received a shipment of equipment packed in heavy-duty laminated cardboard containers, big cylindrical drums used for moisture-sensitive materials. They were sturdy enough to survive transatlantic shipping. They were designed to hold liquids if properly sealed. And they were, fundamentally, expendable. Once empty, they went into the scrap pile. Davis looked at those containers and thought about fuel tanks. Paper had advantages that metal didn't. It was light, dramatically lighter than steel or aluminum of equivalent strength. It was cheap, absurdly cheap compared to machined metal components. It could be manufactured quickly using existing industrial processes. And because it was cheap and quick to make, you could afford to make tanks that were bigger, much bigger, than metal tanks. If a pilot jettisoned them over Germany, you weren't losing $180 of precision equipment. You were losing maybe $15 of treated paper and sealant. But could paper hold gasoline? Could it hold gasoline under pressure, at altitude, in sub-zero temperatures? Could it hold gasoline for the 3 to 4 hours needed for a mission into Germany and back? Davis thought it could, if you built it right. If you used heavy laminated stock, multiple layers bonded with waterproof adhesive. If you sealed it properly with aviation-grade sealant. If you understood that the tank didn't need to be perfect, it just needed to be good enough for one flight. His commanding officer would never approve testing. The engineering brass would laugh at the idea. So Davis did what mechanics have done since time immemorial when they have an idea that officially doesn't exist. He built it anyway. He started in early February, working after hours in one of the maintenance hangars. He requisitioned heavy paper stock, the kind used for moisture barriers in equipment crates. Nobody questioned a crew chief requisitioning materials. He found a local British supplier near Ipswich who manufactured laminated cardboard containers for chemical storage. He bought samples with his own money, then figured out how to get the supplier onto the base's approved vendor list. He borrowed metal end caps from damaged drop tanks sitting in the salvage pile. He permanently borrowed aviation sealant from the supply depot, 8 gallons of it over 3 weeks, in quantities small enough not to trigger inventory audits. The first prototype took him 3 nights to build. It was crude, a cylinder approximately 4 feet long and 18 inches in diameter, made from laminated cardboard stock reinforced at the stress points, sealed at the seams, with simple metal caps at each end for the fuel lines. It looked like something from a high school shop project. It held 165 gallons. He filled it with water first. Water is heavier than gasoline, 8.3 pounds per gallon versus 6, so if the tank could hold water without leaking or structural failure, it could hold fuel. He left it sitting in the hangar for 2 days. No leaks. He had one of the ordnance crews pressure test it to simulate altitude. No leaks. He drained it, dried it, and filled it with aviation gasoline drawn from the fuel trucks after hours. Let it sit for another 2 days. The paper swelled slightly as the fuel soaked into the outer layer, but the laminated construction held. No leaks. The second prototype was larger, 200 gallons. Same construction method, scaled up. Also no leaks. Now he needed to test them on an actual aircraft. He needed a pilot willing to risk his career, possibly his life, on paper fuel tanks built by a mechanic in an unauthorized experiment. He needed Lieutenant Thomas Hayes. Hayes was 23 years old, from Michigan, a fighter pilot with the 357th 364th Fighter Squadron. He was known among the ground crews as one of the more approachable officers, the kind who'd actually talk to the mechanics, who'd listen when they explained what was wrong with his aircraft, who understood that the men who kept the planes flying knew things worth knowing. He was also known as slightly reckless, in the way fighter pilots often are, which in this case was an advantage. Davis approached him in the enlisted men's club one evening in late February. The conversation was brief. "Lieutenant, I've built something, can't tell you what, can't tell you why, but if you're willing to take a flight tomorrow morning, just a range test over the North Sea, nothing official, I think you'll find it interesting." Hayes looked at him. "Sergeant, are you asking me to test something that hasn't been approved through proper channels? I'm asking you to help me prove something that the command doesn't know they need yet." Hayes grinned. "What time tomorrow?" "The morning of March 3rd. Hayes arrived at the hard stand at 0600 to find his P-51B fitted with 2 enormous cylinders under the wings. They were painted standard olive drab. They looked, he would later recall, like someone had bolted tin cans to a racehorse. Davis explained the concept. Paper tanks, 165 gallons each, plus the internal 180 gallons, that was 510 gallons total. At standard cruise consumption of about 60 gallons per hour, that was theoretically 8 hours of flight time, minus reserves. More than enough to reach Berlin and return with fuel to spare. "Paper," Hayes said. "Laminated paper," Davis corrected. "Treated. Sealed. Strong as it needs to be. And if they fail at altitude, then you jettison them and come home on internal fuel, same as you do with metal tanks." Hayes walked around the aircraft, examining the tanks. Touched one. It flexed slightly under his hand. "Jesus, Ben, they'll work. You're betting my life on that." "I'm betting mine. If these fail and you crash, I'm court-martialed. If they work, maybe we stop watching bomber crews die every week." Hayes looked at him, nodded. "Let's fly." The flight plan was simple. Take off, head due east over the North Sea, maintain cruise speed and altitude, burn fuel, and return. No combat maneuvers, no high-stress testing, just endurance. Hayes would burn through the drop tanks. First, the fuel system was designed to use external tanks before, internal then return on the internal fuel supply. If everything worked, he'd land with the internal tanks partially full. If the paper tanks failed, he'd jettison them and still have enough internal fuel to make it home. At 0645, Hayes started the Merlin engine. The propeller blades bit into the cold morning air. He taxied to the runway, performed his pre-takeoff checks. The aircraft handled normally, despite the unusual weight. At 06:52, he opened the throttle and began his takeoff run. The P-51B was heavy, noticeably heavy. The takeoff roll was longer than normal, and Hayes could feel the sluggish response as the aircraft struggled against the weight of 510 gallons of fuel. But the Merlin engine had power 1,400 horsepower, and the runway at Leiston was long. At 95 miles per hour, the Mustang lifted off, climbed slowly, gear retracting. Davis watched from the hardstand until the aircraft was a speck against the gray sky. Then he waited. He waited through breakfast, which he didn't eat. He waited through the morning briefing for the regular missions, which he didn't attend. He waited in the maintenance hangar, checking and rechecking calculations he'd already done 100 times. 165 gallons per tank. Call it 1,000 pounds per tank. 2,000 pounds total. Well within the P-51's maximum takeoff weight. The drag coefficient was higher than streamlined tanks, yes, but not catastrophically higher. The fuel consumption would increase slightly to overcome it, but not enough to negate the advantage of the extra capacity. The numbers worked. On paper, they worked. Now they needed to work in the air, at 300 miles per hour, at 20,000 feet, in sub-zero temperatures. At 10:30, the radio in the operations building crackled. Hayes's voice calm. Leiston Tower, this is Crimson Leader, 20 miles out, requesting landing clearance. 4 hours and 20 minutes since takeoff. He'd been gone longer than any P-51 from the 357th had ever stayed airborne on a single flight. The Mustang appeared as a dot on the horizon, grew larger, dropped toward the runway with gear extended. The landing was smooth. Hayes was a skilled pilot, and despite the unusual fuel load, the aircraft handled predictably. He taxied to the hardstand where Davis waited. Engine shut down, propeller spinning down to stillness. Hayes popped the canopy, stood in the cockpit, pulled off his leather flying helmet. His face was red from the cold and the oxygen mask, but he was grinning. "Ben," he said, "your tin cans just changed the war." The fuel gauges told the story. The paper drop tanks had fed properly through the entire flight. No leaks, no failures, no problems. Hayes had burned through all 330 gallons in the drop tanks, then switched to internal fuel for the return flight. He landed with approximately 70 gallons remaining in the internal tanks, more than enough for a safety margin. Total fuel available, 510 gallons. Total fuel consumed, roughly 440 gallons. Enough for Berlin, enough for Munich, enough for targets that had been unreachable since the war began. And the paper tanks had performed flawlessly. Within 24 hours, Davis was explaining his design to Colonel Henry Spicer, commanding officer of the 357th Fighter Group. Within 48 hours, samples were being packed for shipment to Wright Field in Ohio. Within 72 hours, engineers from the Materiel Command were at Leiston, examining the tanks, running tests, and asking questions. Davis expected skepticism. He got an enthusiastic interrogation. The engineers understood immediately what he'd accomplished, not because the tanks were sophisticated, but because they were perfectly suited to their purpose. They weren't optimal, they were adequate, and adequate at scale was revolutionary. The engineers from Wright Field arrived at Leiston on March 8, 1944. 3 of them, led by Major Robert Scherer from the Materiel Command's fighter branch. They were not pleased. They had spent months, years, in some cases working on the drop tank problem, pursuing advanced materials and sophisticated aerodynamic designs. Now a crew chief with a high school education was claiming to have solved it with paper and glue. Scherer's first comment, upon seeing Davis's prototype tanks, was unprintable in official reports. His second comment was, "Sergeant, do you have any idea how many regulations you violated building these?" Davis, standing at attention because Scherer was a major and Davis was a staff sergeant, replied, "No, sir, probably several." "And do you have any idea how much we've spent trying to develop tanks that can do what you claim these can do?" "No, sir." Scherer walked around the tanks for a full minute without speaking. Then he turned to Davis. "Show me your calculations." Davis didn't have calculations. He had sketches on the backs of requisition forms and a working knowledge of how containers behaved under pressure. He explained his reasoning, the weight advantage of paper, the cost advantage, the disposability factor, the lamination technique, the sealing method. He showed them the pressure tests he'd run. He showed them Hayes's flight logs from the March 3rd test. Scherer listened. Then he said, "We're taking these back to Wright Field. And Sergeant, you're coming with them. You're going to explain this to people who are going to be very unhappy with you." The tests at Wright Field began on March 13th. The Army Air Force's Materiel Command had extensive facilities for evaluating aircraft components, wind tunnels, structural testing equipment, environmental chambers, everything needed to determine whether Davis's paper tanks would actually work under operational conditions or simply disintegrate at 20,000 feet over Germany. The first test was structural. They mounted a tank in a compression frame and applied gradually increasing pressure until it failed. The tank held to 14 pounds per square inch before the seams began to separate. At operational altitude, a sealed fuel tank would experience roughly 5 to 6 pounds per square inch of internal pressure from fuel vapor. Adequate margin. The second test was environmental. They placed a fuel-filled tank in a cold chamber and dropped the temperature to -40 degrees Fahrenheit, typical for high-altitude flight in winter. Left it for 6 hours. The fuel didn't freeze. Aviation gasoline has a much lower freezing point than water, but the paper could have become brittle. It didn't. The laminated construction remained flexible. The third test was the wind tunnel. They mounted tanks on a P-51 airframe mock-up and measured drag at various airspeeds. The results surprised everyone. Davis's cylindrical tanks, with their blunt shape and complete lack of streamlining, produced less drag than expected at cruise speeds above 250 miles per hour. The rough paper surface created micro-turbulence, tiny vortices in the airflow that paradoxically reduced the overall pressure differential. It was the opposite of what sophisticated aerodynamic design tried to achieve, and it worked better. Major Scherer wrote in his report, "The Davis Patton tank represents a counterintuitive solution to the range problem. By abandoning optimization in favor of adequacy, and by accepting expendability as a design feature rather than a flaw, Sergeant Davis has achieved what our best engineering efforts could not. These tanks should be put into immediate production." On March 22, 1944, the Army Air Forces issued a contract to the Continental Can Company of Chicago. Continental Can was not an aviation contractor. They made tin cans, cardboard containers, and paper products, but they had the machinery and expertise to mass produce laminated paper cylinders. The initial order was for 20,000 units designated expendable fuel tank, paper composite, 165-gallon, type B2. Cost per unit, $11.50. An aluminum drop tank cost $180. A pressed steel tank cost $75. Davis's paper tanks cost less than the fuel they carried. Continental Can delivered the first production batch on April 15th. By May 1st, P-51 groups across England were receiving them. By May 8th, 6 months before the Normandy invasion, the 8th Air Force flew its first long-range bomber escort mission to Berlin with Mustangs carrying Davis Patton tanks. The results were immediate and dramatic. On May 8, 1944, over 400 B-17 and B-24 bombers struck targets in Brunswick and Berlin. They were escorted by P-51 seconds carrying paper drop tanks, fighters that could now stay with them all the way to target and all the way back. The Luftwaffe intercepted, as always. But this time, instead of waiting until the escorts turned back, the German fighters found themselves engaged over their own airfields by Mustangs that weren't running out of fuel. The 8th Air Force lost 13 bombers that day. In October 1943, they had been losing 60 to 70 bombers per mission. The loss rate had dropped from 20% to less than 3%. It stayed low. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The mathematics of the strategic bombing campaign changed in the spring of 1944, and paper fuel tanks were central to that change. Before long-range escorts became available, the 8th Air Force had been losing an average of 176 heavy bombers per month, destroyed, written off, too damaged to repair. That represented roughly 1,800 American airmen killed or captured every 30 days. At that rate, the casualty projections for completing the strategic bombing campaign exceeded 40,000 dead. After P-51 seconds equipped with Davis Patton tanks began flying deep escort missions, the monthly loss rate dropped to 58 bombers, a 67% reduction. Over the course of 1944, That difference represented approximately 8,000 American airmen who flew missions into Germany and came home, instead of dying in the wreckage of burning bombers. But the impact went beyond simple loss reduction. The long-range escorts changed German defensive calculations. Before May 1944, the Luftwaffe fighter force could concentrate against bomber formations with reasonable confidence that the American escorts would turn back at the border. German fighters could refuel, rearm, and attack again during the bombers' withdrawal. It was a sustainable defensive strategy. After May, Luftwaffe fighters faced continuous engagement from the English coast to the target and back. They couldn't break off to refuel without leaving the bombers undefended. They couldn't concentrate their forces because the escorts were everywhere. German fighter losses, which had been manageable through early 1944, became catastrophic. By June, the Luftwaffe was losing fighters faster than they could train replacement pilots. By July, German daytime air superiority had effectively ended. The strategic bombing campaign, which had been on the verge of abandonment in March 1944, became the decisive factor in destroying German industrial capacity. Oil production collapsed under sustained attacks. Aircraft production, which Germany had managed to increase through early 1944 despite bombing, was finally disrupted as raids hit component suppliers. Transportation networks fractured. By December 1944, German war production had dropped to 60% of its peak. None of that happens without fighter escorts reaching the targets. None of those escorts reached the targets without additional fuel capacity. And the fuel capacity that made the difference, the capacity that turned the P-51 from a 400-mile interceptor into a 1,600-mile escort fighter, came from paper cylinders that cost $11.50 each. Benjamin Davis received a commendation from Colonel Spicer on May 20, 1944. The citation praised his initiative, technical innovation, and contribution to combat effectiveness. He was promoted to technical sergeant. His base pay increased from $112 per month to $138 per month. That was the extent of his official recognition. In June 1944, as D-Day approached and Allied air superiority over France became absolute, the Army Air Forces issued a press release about the P-51's extended range capability. The release mentioned improvements in fuel capacity and enhanced drop tank technology. It credited engineering teams at Wright Field and contractor facilities with developing the new tanks. It did not mention Benjamin Davis. Continental Can Company took out a full-page advertisement in Aviation Week magazine in July 1944. The advertisement showed a formation of P-51 seconds escorting B-17 seconds with the headline, "Continental Can, helping our fighters go the distance." The ad copy described the company's rapid mobilization to produce fuel tanks for the war effort. It mentioned their production capacity, over 100,000 tanks manufactured by July, and their contribution to Allied air superiority. It did not mention that the tank design came from a mechanic in England, not from Continental Can's engineering department. In August 1944, North American Aviation published a technical bulletin describing improvements to the P-51's operational range. The bulletin detailed the ferry range, the maximum distance the aircraft could fly without combat maneuvering or reserves, which now exceeded 1,600 miles with external tanks. The document credited collaborative efforts between North American Aviation, the Army Air Forces Materiel Command, and approved contractors. In the footnotes, under a section titled Tank Development History, there was a single sentence: initial field testing of paper composite tanks conducted by 357th Fighter Group maintenance personnel, March 1944. Davis's name appeared in that sentence. His first name was misspelled as Benjamin when his service records listed him as Benny. But it was there, in a footnote, on page 17 of a 23-page technical document that fewer than 200 people would ever read. That was the closest he came to official recognition during the war. The thing about innovation in wartime is that it becomes absorbed into the machinery of production and bureaucracy almost immediately. A breakthrough doesn't remain attached to its creator, it becomes standard procedure, official doctrine, manufacturing specification. This is necessary. War production operates at massive scale, and scale requires standardization, documentation, institutional ownership. There's no time or mechanism for preserving the story of how something was invented when the priority is making 10,000 more of it. By September 1944, Davis pattern drop tanks were so common that new pilots arriving in England didn't know they were called Davis pattern tanks. They were just the standard tanks, the ones that let you fly to Berlin, the ones that every P-51 carried. Ground crews bolted them on, pilots jettisoned them over Germany when the weight wasn't needed, and nobody thought about where they'd come from. They were simply part of how things worked now. Davis himself never spoke much about it. In the culture of military maintenance crews, you did your job. If you had a good idea, you tried it. If it worked, that was enough. You didn't write yourself commendations. You didn't expect parades. The mission was to keep the aircraft flying, and if a paper fuel tank accomplished that better than an aluminum one, then you used paper. The recognition that mattered came from the pilots who returned safely, from the ground crews who saw the mission success rates improve, from the knowledge that fewer bombers were being shot down. That was supposed to be enough. After the war, Davis was discharged in December 1945 at Camp Atterbury, Indiana. His discharge papers listed his service: mechanic, crew chief, 3 years of service, European Theatre of Operations, Good Conduct Medal, European African Middle Eastern Campaign Medal with 3 bronze stars. There was a section for notable achievements or commendations. It was blank. The bureaucracy that processed thousands of discharges per week had no mechanism for capturing something as specific as invented the fuel tank that changed the air war. He took the train back to North Carolina, used his GI Bill benefits to open a garage in Wilkesboro Davis Automotive Repair. He married in 1947, had 2 children, lived a quiet life fixing cars and farm equipment. When veterans groups met, he attended occasionally, but he didn't tell war stories. When people asked what he'd done in the war, he said he'd been a mechanic in England. True enough. In 1953, a feature film was released, The Command Decision, starring Clark Gable as a bomber commander facing the crisis of unsustainable losses over Germany. The film depicted the October 1943 raids, the devastating casualties, the debate over continuing the bombing campaign. Near the end, the Gable character receives news that new long-range escort fighters are arriving, P-51 seconds with improved range. The bombers launch again, this time with escorts that can reach the target. The missions succeed. The war turns. The film was praised for its realism and its depiction of command pressure during wartime. It won an Academy Award for cinematography. In the closing credits, there was a note thanking the Army Air Force's Historical Division for technical assistance. The film did not explain how the P-51 seconds achieved their extended range. It did not mention drop tanks, paper or otherwise. The solution to the crisis was presented as simply better fighters arriving, as if range were a feature that came standard, as if someone hadn't had to invent the solution. In 1963, a reporter from the Wilkes Journal Patriot was doing a feature on local D-Day veterans for the 20th anniversary of the invasion. He interviewed Davis because someone had mentioned he'd served in England during the war. Davis talked about the airfield, the maintenance work, the weather. When the reporter asked if he'd contributed to any specific technical developments, Davis mentioned the fuel tanks. He explained the concept, the testing, the results. The reporter didn't understand. He asked, "But weren't those tanks already standard equipment? I thought P-51 seconds always had a long range." Davis tried to explain that they hadn't, that the range limitation had been a critical problem, that someone had needed to solve it. But the context wasn't there. 20 years after the war, the public understanding was that P-51 seconds were long-range escorts. That was simply what they were. The idea that they'd once been limited, that there had been a crisis, that someone had solved it, all of that had been compressed into historical background. The article ran in the journal Patriot on June 6, 1963. It was titled, "Local Veterans Remember D-Day." Davis got 3 paragraphs. The fuel tanks weren't mentioned. The reporter had decided it was too technical, too confusing for general readers. In 1974, the Air Force Museum at Wright-Patterson Air Force Base in Ohio opened a new exhibit on World War II fighters. The centerpiece was a restored P-51D Mustang, suspended from the ceiling, with original drop tanks mounted under the wings. The placard beneath it read, "North American P-51D Mustang, the premier American fighter of World War II. Range, 1,650 miles with external fuel tanks." The P-51's extended range capability made it the ideal escort fighter for long-range bomber missions deep into German territory. The placard mentioned North American aviation. It mentioned the Rolls-Royce Merlin engine. It mentioned the 8th Air Force and the strategic bombing campaign. In small print at the bottom, it noted that the drop tanks were paper composite construction, manufactured by Continental Can Company, 1944 to 1945. There was no mention of how that design came to exist, no mention of the crisis it solved, no mention of Benjamin Davis. In 1979, Davis died of heart failure at the age of 67. His obituary in the Wilkes Journal Patriot ran 4 sentences. Benjamin Clarence Davis, 67, of Wilkesboro, died Tuesday at Wilkes General Hospital. He was a veteran of World War II and owner of Davis Automotive Repair. He is survived by his wife, Margaret, 2 sons, and 4 grandchildren. Services will be held Friday at First Baptist Church. No mention of fuel tanks. No mention of strategic bombing. No mention that his idea had saved thousands of lives and changed the course of the air war over Europe. His family knew, of course. His sons knew their father had done something important during the war, something involving airplanes and fuel. But Davis had never made much of it, and the family took their cue from him. It was something Dad had done, back in the war, when he was young. He'd been proud of it, in his quiet way, but it wasn't something to make a fuss over. After his death, his widow found a box in the garage. It contained his discharge papers, some photographs from England, a commendation letter from Colonel Spicer, and a technical drawing one of the original sketches Davis had made of the fuel tank design on the back of a requisition form dated February 1944. She kept the box. Eventually it went to one of the sons, then to a grandson. The family understood it was important somehow, though the context had faded. In 1995, a graduate student at the Air Force Institute of Technology was researching the development of drop tank technology for his master's thesis. He was working through declassified documents at the Air Force Historical Research Agency when he found a March 1944 memo from Major Scherer at Wright Field. The memo described tests on paper composite tanks developed by S. Sergeant B. Davis, 357th Fighter Group, and recommended immediate production. The student was intrigued. This didn't match the standard history, which credited the Army Air Force's engineering teams with developing improved drop tanks in early 1944. He dug deeper, found Hayes's flight test reports, found production records from Continental Can, found the technical bulletin from North American Aviation with a single footnote mentioning the 357th Fighter Group. He tracked down the unit records for the 357th, found Davis's name in the personnel roster, found the commendation from Spicer, found nothing else, no interviews, no post-war documentation, no historical marker. He tried to find Davis himself. Discovered he'd died in 1979. I tried to find family members. By 1995, the trail was cold. One son had moved to Florida, contact information unknown. The other had died in a car accident in 1988. The grandchildren had scattered. Nobody he contacted remembered anything specific about fuel tanks. The student's thesis, completed in 1996, included a chapter on the Davis pattern tanks. He argued that the standard history of P-51 range development had overlooked a critical field innovation by a non-commissioned officer. The thesis was filed in the Institute's library. Approximately 15 people read it. In 2003, the Smithsonian's National Air and Space Museum updated its World War II gallery. The P-51 exhibit was expanded. A new placard was added, discussing the development of extended range capability. This version mentioned that improved fuel tank designs were developed through collaboration between Army Air Forces engineers and field maintenance personnel. It was a slight acknowledgement that the innovation had come entirely from formal engineering channels, but it still didn't name anyone. In 2008, a military history enthusiast and amateur researcher named James Callahan was reading through declassified Army Air Forces documents posted online by the National Archives. He came across Scherer's March 1944 memo. The name B. Davis caught his attention because his own grandfather had been a mechanic with the 357th Fighter Group. Callahan started pulling threads, found the graduate thesis from 1996, found a digitized copy of the Spicer commendation letter, found Davis's service record, now available through an online database, found the obituary from the Wilkes Journal Patriot, preserved in a newspaper archive. He wrote an article for a military aviation history website titled the mechanic who extended the P-51's range. It included everything he'd found: the context of the crisis, the engineering deadlock, Davis's unauthorized testing, the production rollout, the impact on the air war. It was thorough, well-researched, carefully footnoted. The article was posted in November 2008. It received about 3,000 views over the following year. Several dozen comments from aviation enthusiasts, most saying they'd never heard this story before. A few commenters questioned whether a single mechanic could really have developed something that formerly trained engineers couldn't. One commenter, a retired Air Force engineer, replied that yes, that's exactly how breakthrough innovations often happen in the field, when someone isn't constrained by institutional assumptions about how problems should be solved. In 2011, one of Davis's grandsons living in Arizona, working as a software engineer, was searching online for information about his grandfather's war service. He found Callahan's article. He read it twice, then called his brother. "Did you know what Grandpa actually did during the war?" The brother hadn't. Their father had mentioned something about fuel tanks, but never with any detail. They'd always assumed it was routine maintenance work. The grandson reached out to Callahan, sent him the sketches and documents from the box their grandmother had saved. Callahan scanned everything, added it to his article as an update. The original requisition form sketch, Davis's hand-drawn design, became a minor internet artifact, the kind of thing that circulates among military history enthusiasts as an example of wartime innovation. In 2015, the Air Force Museum at Wright-Patterson added a small supplementary placard to their P-51 exhibit. It read, "The paper composite drop tanks that extended the P-51's range were developed by S. Sergeant Benjamin Davis, a maintenance crew chief with the 357th Fighter Group, in March 1944. His field innovation solved a critical range limitation that had prevented effective bomber escort deep into German territory." It was 60 words. It was 71 years after Davis built his first prototype. It was 36 years after his death, but it was there. The thing about history is that it's simultaneously comprehensive and selective. We preserve vast quantities of data unit records, production figures, after-action reports, technical specifications. We can tell you how many bombers were lost on any given mission, what the operational ceiling of a P-51B was, how many drop tanks. Continental can, manufactured per month. The data survives. But the stories behind the data, the human decisions, the unauthorized experiments, the mechanic working after hours because he thought he had a better idea, those stories survive only through deliberate effort. They have to be recorded, preserved, retold. They have to matter to someone enough that they fight against the natural entropy of historical memory. Benjamin Davis's story nearly didn't survive. It exists now in fragments, declassified memos, a graduate thesis, an amateur historian's website article, a small placard in a museum. It exists because a few people found pieces of it and recognized that those pieces revealed something important, that war is won not just by the people making grand strategic decisions, but by the people solving mundane technical problems in cold hangars at 0200 in the morning. The P-51 Mustang is remembered as one of the great fighters of World War II. Its image appears in countless documentaries, museum exhibits, and historical publications. When people think of American air power in Europe, they think of Mustangs escorting bombers to Berlin. The long-range escort capability is described as if it were inherent to the aircraft, as if it simply came that way. But it didn't come that way. Someone had to make it that way. Someone had to look at a problem that trained engineers had declared unsolvable and think, what if we're solving the wrong problem? What if instead of building better tanks, we build adequate tanks that we can afford to throw away? That someone was a mechanic from North Carolina who understood moonshine stills and crop dusters, who knew that sometimes the perfect solution costs too much and the adequate solution is what wins. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.